start looking at topology. Topology is basically set theory on steroids, so we're going to start at the beginning with set theory. Set theory starts out simply, but very quickly gets very difficult, obscure, and abstract. Some of these concepts seem very straightforward if you only glance at them, but if you really try to nail them down, they can be downright mind-bending. Wait till we get to the set theory definition of an ordered pair. It's important for us to start at the beginning because, as I've said several times in these videos, I don't think there's anything in math that's going to be beyond our grasp. It's a question of understanding everything thoroughly step by step. Myself, every weakness I have stems from going over things too quickly in class so you don't really absorb them, and then 2 years later you're studying something that relies on you having a thorough understanding of what you were supposed to have learned earlier. Over time, your understanding becomes shakier and shakier, and it's not because the thing you're learning now is hard, it's because you glossed over some previous foundational concepts. Okay, so this video is about set builder notation. We run into trouble almost before we're out of the gate because set builder notation is very poorly defined and ambiguous. We're going to fix that right here and now with two refinements to set builder notation that will clarify a lot of the confusion and ambiguity and put set builder notation on a firm, unambiguous foundation that will make a lot of bad math writing a lot easier to read from this point forward. One last comment before we get started. As you're probably aware, there are some logical questions involving the axioms that make up set theory. It's possible to construct logical contradictions. For instance, Russell's paradox, Gödel's incompleteness theorem, the Banach-Tarski paradox. But those questions are really about the foundations of math and mathematical logic. They're fun questions to contemplate, but I think we have bigger fish to fry. So we're not going to spend any time on the logical foundations of set theory. As long as we're clear on what our assumptions are, we don't have anything to worry about. Okay, so anyway, set builder notation. We will use capital letters to denote sets, lowercase letters to denote objects or elements belonging to sets. And then if an object A belongs to a set capital A, then we write it like this, that A is an element of A. And then if A does not belong to A, we write that it does not belong to A. So then A equals B means that A and B are both symbols for the same object, similar to what we mean when we say like that 2/4 equals 1/2. So the A and the B are not the objects themselves, they're symbols that represent the objects in the set. And then set A equals set B means that capital A and capital B are symbols for the same set, meaning that the two sets consist of precisely the same objects. We used this concept a lot when we were proving the uniqueness of the real numbers, so this is familiar to us. So if A and B are different objects, then A does not equal B. If the sets are different, then A does not equal B. We say that A is a subset of B if every element of A is in B, and we write that like this. And then this means that A and B may be equal, or B may have more elements than A, but every element of A is in B. And then if A is a subset of B, but A is different than B, then A is a proper subset of B, and we write that like this. And so this is called inclusion, and this is called proper inclusion. And then if A is a subset of B, then we can also say that B contains A. And then note just quickly again that some authors use this symbol to mean subset or equal. And then if they want it to be a proper subset, they have to use words to say proper subset. But we're going to do it this way because it's more explicit, and also it kind of evokes less than or equal than and less than, so it's a little more clear, I think. But remember, this means that it's not equal. Okay, set builder notation. So there are two ways to specify a set. If the set has only a few elements, one can simply list the objects in the set, writing A is the set consisting of the elements A, B, and C. So in symbols, that statement would be A equals ABC, where braces are used to enclose the list of elements. Some people call this roster notation. The more common way to specify a set, however, is called set builder notation. Basically, you take some set A of objects and some property that elements of A may or may not possess, and you form a set consisting of all elements of A having that property. For example, so here the braces stand for the words the set of, and the vertical bar stands for the words such that. So this would be read as B is the set of all X such that X is an even integer. So this notation, even though it's completely standard, is very problematic because the rules of this notation are too vague and open-ended, allowing for huge discrepancies in how it's used, which can create unnecessary and avoidable obscurity and confusion. Remember, you get points for clarity, not brevity. So I'm going to present here two modifications to the standard rules for set builder notation that we will be using moving forward that should help to avoid some of the more egregious problems with this notation. So I've found at least 7 different and sometimes even contradictory forms of set builder notation. Let me write them down first, and then we'll discuss them. Okay, so every one of these does something different. So one, of course, is the standard basic notation. This is the one that they tell you to trick you into thinking that this notation is simple and sensical. 2 specifies the larger set from which we're choosing objects. In topology, this is very important. As we'll see, even the definition of an open subset changes depending on which set you're taking the open subset from. But this notation doesn't actually make any sense at all, given what we said the definition of set builder is. The property you are applying to elements of the set should be on the right. You can write this set equally correctly by saying that it's X such that X is an element of R and X is an even integer, right? So there's a reason to put is an element of R on the left to emphasize the set that is the context of this set that we're building. But this makes the notation completely arbitrary. Some authors might put it on the left, some put it on the right, and some might just put it in the paragraph describing the set. And that's what Monkrez usually does in his topology book. He'll say, let X be a topological space, then U is a subset of X, meaning this subset is within the context of the larger set X. In addition, this notation simply breaks the rules of set builder notation. Properties don't go on the left, they go on the right. So we're going to adopt a different notation to specify the larger set we're dealing with, which I'll show you in a minute. But first, let's go on and look at the rest of the examples. So 3, 5, and 6 I took from Monkrez. And this one defines a product topology, this one is a subspace topology, and this one is a subbasis for the product topology. And we'll be getting to these in just a couple weeks. We'll be starting to look at what all this means, but in the meantime, we're just looking at how they're defined right now. So this one does something completely different from what we've looked at so far. It seems to be specifying the form of what the elements of this set are going to look like. Nothing in the definition of set builder notation allows for that. The elements here will be a Cartesian product, B cross C. So you have the properties on the right that B is an element of B and C is an element of C, and then you put them together to form the elements of this set. So that's okay, but it's definitely different from these two. Okay, let's look at 6 and then we'll come back to 4 and 5. So 6 is doing something completely different yet again, because this one isn't specifying the form that elements of this set are going to take the way we did up here. This is taking the elements that satisfy the property on the right, open sets of X, and it's running them through a function. So this isn't defining the form of the elements of the set, it's actually doing something to the elements that satisfy the property on the right, and the elements of the set then are the output of this function. Okay, so what about 4 and 5? So 4 defines rational numbers. And I think you could see this one in either way. I think you could read this in either way. You could argue that P over Q is simply the form that elements of this set are going to take, integer over integer. Or you could argue that this is a function. You plug in P and Q and it spits out a fraction, P over Q. So what about 5? So it's y intersected with u where u is an element of t. So this doesn't really define the form of the elements like b cross c or p over q, but is y intersected with u a function? Yes, it is a function. The difference between this one and 6 are that here the body of the function or the definition of the function is stated inside the set notation rather than as in 6 where the function is defined elsewhere. Okay, so with all this in mind, let me take this off. So I'm modifying the standard definition of set builder notation with 2 refinements. First, to address this example where they specify the larger set. If you need to specify the larger set that is the context of the set you're building, put it outside the brackets followed by a colon. So for instance, with this example, we would write that B equals, okay, so you put the context outside of the brackets before a colon, okay, and then this is 2. And then number 6 would be, here again, when it says U is open in X, that's because what it means to be open depends on the enclosing set. So we could rewrite this one as, so here X colon specifies that X is the context of this set, so that U is open means U is open in X. Okay. So secondly, we can put 1, 3, 4, 5, and 6 into one rule. I have not found this stated explicitly anywhere, but we're going to state it explicitly now. The left side of the set builder notation is the definition of something like an anonymous function in JavaScript. That just means it's a function, a programming function without a name. The right side of set builder notation does 2 things. First, it gives names to the input parameters of the function on the left. So it names P and Q, and then we're going to use them over here. Here it names U, and we're going to use them over here. And then it assigns values to the arguments that are going to be passed into that function. So here U is all of the open sets of X. Here P is all of the integers, Q is all of the positive integers. So then the left side of the set builder notation is the actual body of the function. The parameters that are defined on the right are referenced and used and manipulated on the left. And then the return value, that is the value of the element that's added to the new set, is the value that this function returns. So if we look again at our examples, we can see that all 5 of them, 1, 3, 4, 5, and 6, work with this redefinition. So B cross C, you take 2 arguments, B and C, and then return B cross C. P over Q, you take 2 arguments, P and Q, return P over Q. Y intersected with U, you take all of the elements of T and cross them with Y. And then pi sub 1 of U, you take all of the open sets, call them U, and run them through pi. And then the elements of this set are the results of this function. And then note in particular that this one, our basic set builder definition, also works with this definition, with the function simply returning the input. Okay, so this is the way to use set builder notation. The right side does 2 things. It defines the parameters the function on the left will use, B and C, P and Q, X, U, and it specifies the properties that the arguments that will be passed into those parameters must satisfy. So P has to be an integer, U has to be an element of T, and so on. The left side then is a function that takes those arguments, does something to those arguments, and then returns some value which will then become an element of our new set. Okay, so finally, let's look at our last example here. In the last video, we discussed this notation at length. The notation that we were given was that the outer measure of E is the sum, it's hard to even read this. So, oh, I forgot. So the outer measure is the infimum of this set, but the set that we're looking at is we take each sequence of intervals in R that cover E, and then we sum the lengths of all of them. Those are the elements of this set, and then we take the infimum, that's the outer measure of E. So with our new definition of set builder notation, we can point to exactly why this notation is wrong. It's wrong for two reasons. First, it does not label the parameter that it's sending to the left. It describes the elements that satisfy that property, but it doesn't label them. We don't have any way to refer to one of these sequences over here in our function. So you're left with a function over here and no way to refer to the values that you want to pass to it. Secondly, the function on the left does not explicitly refer to the parameter defined on the right. So our new definition requires you to be explicit about the parameter that you're manipulating. It's not possible to use the summation notation as the function of a set builder notation in this way, because in summation notation, the thing that you're summing over is implied. To use a sum in set builder notation, you have to define the function elsewhere and refer to that function in the set builder notation so you can refer to it explicitly. So if we do that, let A be a sequence of intervals of real numbers. Let I sub k be the kth interval in that sequence. Let mu of A equal the sum from 1 to infinity of the lengths of each ik in the sequence. Now we can define the Lebesgue outer measure properly. So the Lebesgue outer measure equals the infimum of this set. So this set is what we're concerned with, but then the Lebesgue outer measure is the infimum of the values in this set. So the set now is all mu of A such that A covers E. Simple and understandable. A can be any sequence of intervals of real numbers. We're looking at the ones that cover E, and then we're running them through this function, and we're ending up with a set of these sums for each A that covers E. Now the parameter A is defined on the right as a sequence of intervals covering E, and the function on the left takes A as input and returns the sum of the lengths of all of the intervals in A. Okay, so I know I'm being pedantic about this, but the notation for the definition of the outer measure really irked me. And since one of the goals of these videos is to demonstrate that 99% of the difficulty in math comes from obscurity, not the difficulty of the underlying material, I want to beat that definition into submission. From now on, think of set builder notation in this way, and recognize when you come across set notation that violates our new rule, and it will help you to parse what the author who isn't doing her job properly is trying to say. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.